Alright, so this is the solution to the 17th problem in the grind 75. This one is called climbing stairs. So basically we are given a value n, and we are able to climb one step at a time or two steps at a time, and our goal is to reach n. So these are two very good examples, and I will actually illustrate n is equal to 3. So we're going to switch over to Paint really quick. So if n is equal to 3, let's get our favorite color. N is equal to 3. And we are at the ground floor, and we have 1 step, 2 steps, and 3 steps. This is where we have to get to. Then, starting from here, we can either take 1 step, another step, and another step. That's one way. Or we can take a single step and 2 more steps, or sorry, a single step and then 2 steps, or we can take 2 steps and then 1 step. And the way that we can break this problem down is by thinking about how many steps we would have if we were already at a certain spot. So if we are at this spot, it's like we're at n is equal to 2, because now we only have 2 more steps to take. So we can either take 2 single steps, or we can take 1 2-step. And that's exactly what the example illustrates, or what the example talked about and what this illustrated. So a good way to visualize this is to use a tree that can show us the different decisions we can make when taking steps. So we're going to start off with 3 as our n, and we can decide maybe we want to go just 1 step, and maybe another decision we could take would be to take 2 steps. So if we were to take 1 step from here, then we would be at n equals 2 again. So we can say like that. But if we were to take 2 steps initially, then we would be all the way up here. We'd be all the way up here, and that would mean we would only have 1 step left to take. So I am going to write that in. And then we can continue this process until we get to one of 2 cases. Once we are here, we know that there is only one way to get up here, right? But if we are here and we decide to take that 2-step, that means we've also reached the top here, right? So that is another way to reach the top. But again, if we are at n equals 2, we can also decide to take just that 1 step. So let's take that 1 step. And these are pretty much our base cases right here, 1 and 0. We know that we'll never go below that, because as soon as we hit a value right above 1 or 0, all we can do is go down to 1 or go down to 0. In either case, those will represent single ways that we can take to get to 3 eventually. So this will add 1 to our total, this will add 1 to our total, and this will also add 1 to our total. So 1 second, please give me a second. All right, so we seem to pretty much get the idea. So I will write out the basic solution, but we're actually going to see that there is one more step to this. So let me switch over to the LeetCode window and basically just write out what we said. So if we get to the point where n is less than or equal to 1, then we know we have found, we've hit the bottom, and that is one way to reach the top. So we can just return 1. Otherwise, what we're going to want to return is the sum of us going down 1 step and also going down 2 steps. And this is, recursion, just applying the same process to the next level down in that tree. And this will actually work, but because as you can see, we can run this example, but when we hit submit, you can see actually from my past submissions what's going to happen. The time limit is exceeded, and that's because when I will switch back to the paint really quick. When we have numbers that are extremely large, like say we have, let me see, give me 1 second, I lost my pen. Okay, so when we have numbers that are very large, I'll draw out 4 really quick. So 4 is going to branch off into 3, 2, which is going to be 2, 1, going to be 1, 0, it's going to be 1, 0. When we get a number that's extremely large, we will have to basically redo operations that we've already done. So if we have a number like, say, yeah, this for example, when we make the recursive call, we're going to be doing the n-1 step first. So we're going to be going down this route. And once we hit the base case, then we're going to move on to the n-2 section. And as we are summing the recursive calls, we're going to get values for each n level. So we're going to get a value for 2, and then 1 for 3, and so on. But the thing is, when we make these recursive calls, these same low-level recursive calls are going to be made later on in the tree because of the steps that we will be taking, because we're only taking, we're going down by 1 or by 2. So there's going to be a ton of overlap. And if we think about how big this can get if we move on to something like this, we will have to do this entire 3 tree again. Sorry, that was it's not a great circle. We'll have to do this entire 3 tree again over here. And you can just imagine how expensive that's going to be in the long run. So something that we can do to reduce cost is to store this sum as soon as we get it. And actually do that for every sum as soon as we get it, unless of course it's a base case. And the way that I decided to do it was to create a hash map, which, let me switch over. So I created a hash map with a key of the nval, and the value is just going to be the sum. So up here, I created a public hash map. It's going to be type integer, where integer is the n value, and the second integer is the sum. And I'm going to call it cache. Just kind of like a local, like short-term memory kind of thing. And we're going to create this hash map like so. And we're going to say, so if we haven't hit the base case, then the first thing we're actually going to do is check if cache has our corresponding n value in it. So if cache.contains key, the current n value we're on. If that's the case, then we can do a constant time operation to simply look up its value, which will be the correct sum. So we can return cache.get n, like so. Otherwise, I'm going to create an integer called, let's call recursive call sum. That's going to be equal to this right here. And if we have gotten to the point where it's not in our cache yet, like say we had gone down that left side of the tree and that was the first time we're seeing that value, then we're going to want to add it to our cache. So we're going to say cache dot put. We're going to put in our current n value, and we're going to put in recursive call sum. And then we're going to have to eventually return recursive call sum to get our initial, the value that we really want for our initial n. And as we can see, this runs normally for test cases, and it runs a lot faster for, yeah, see, runs a lot faster for the actual submission. All right, so this has been the solution to the 17th problem. 14, 15, 16, 17. Yeah, 17th problem in the grind 75.